I don't.
Okay. Yesterday, I know we talked about this in first period. I don't remember if we talked about it in this class yesterday, but there was a function towards the end of yesterday's lecture. That was 3x to the fourth plus 4x cubed minus 7x squared minus 2x minus 3. And they asked you to use, I think, -2 and 3 to show with the upper bound and lower bound theorems that there are no zeros to the left of -2 and there are no zeros to the right of +3. So we went through the synthetic division and we proved that. Okay, we saw that with 2 in my box here. That synthetic division provides all positive quotient lines or quotient values. So that tells us that that +2 is an upper bound. Okay. We also then tried -3, and we saw that they alternate in sign, and I said that that is a lower bound. So we don't have any zeros that exist outside -3 to 2. Does that make sense? Okay. That's what we talked about yesterday. But then we got to the graph, and again, I'm not sure 100% sure if we use this one in this class. But when I look at that graph there, our next task was to not only know that -3 and 2 were going to be kind of the restriction on where our zeros occur, but our next thing is to go find those zeros, right? And we go through and we talk about looking at this function again, and we look at the p-values. So the factors of -3 are +1, -1, +3, -3. And then we look at the factors of your a coefficient, your a sub n coefficient, and that's +1, +3. So if you think about anything p over q, your values of p over q are going to be +1, -1, +3, -3, and then +1/3, -1/3. Those are your options, right? If we go through and we look at this picture, none of those values show up, right? Okay. Obviously, 1 and -1 are not being zeros. Okay. The -3 and the +3 are not being zeros. And then we see our only options and what would be left over would be 1/3 and -1/3, and those are not being zeros being used there. But remember what the rational root theorem says. The rational root theorem says these are potential rational zeros. Okay? Doesn't mean that they all are zeros. Does that make sense? And it doesn't mean in that list that you're going to have anything that shows up to be a zero. That's an example where that list of P over EQ is exhausted. And you go through all of them, and none of them show up to be zeros. So, what are those zeros then? Okay? Because these are, we zoom in, those are zeros right there and right there. They physically cross the x-axis, right? But if they're not rational zeros, what do they have to be? They have to be irrational. Okay? Now, if they're irrational, then we've got some work to do to find them. Okay? And really the work to do to find them, sometimes we'll go through that work and it'll be something that we can do. But in general, if I start with an x to the 4th polynomial and I have just irrational solutions, there's going to be situations where that's hard for us to find those. Okay? There are algorithms, there are procedures that allow you to do that, but for the most part, we're focused on finding real zeros, and then occasionally there might be a byproduct of finding a couple real zeros that lead us to a couple irrational zeros. Okay? In this situation, it's kind of hard to get a starting point. Does that kind of make sense? Okay. If I had a real zero in there, it would depreciate my 3x to the 4th to a cubic, and then maybe find another zero. It would depreciate that cubic to a quadratic, and then once I get to a quadratic, we could use all of our factoring tools and techniques to find irrational zeros with the quadratic formula. Okay. But other than using the quadratic formula, we struggle being able to find those irrational zeros. So I just wanted to make that clear, that the rational root theorem is just kind of a test. It's a starting point for us. If you look on 3-4 maybe, I wrote this explanation. It says the rational roots or rational zeros test is a handy way of obtaining a list of useful first guesses when you're trying to find the zeros or the roots of a polynomial. Okay? They're not necessarily going to be solutions. Okay? They're not necessarily going to be zeros. They're just giving you a good starting point. Does that kind of make sense, everybody? I think in the past and in the last couple of days, people ask me, questions that kind of elicit a thought in my mind that we maybe don't necessarily, and it might have been because I didn't describe it well enough, people are thinking that they should, every single time they get P over Q, there should be values in there that always work. Okay? They don't. It just means if there are zeros, they're going to be of that form P over Q. Does that make sense? And if they're rational zeros. Okay, so hopefully that clears things up a little bit. If you've been working on that stuff in that homework, you've got questions on it, we may have time at the end to talk about some of those questions, but I am going to extend last night's homework until one more day. So I think it's due tomorrow, so I'll push it back to Thursday so we can ask questions tomorrow about it in class first thing. But today's stuff, section 3.5, is simply an extension of what we've been doing. So I do think it's appropriate while it's fresh in our mind with the synthetic division and with this factoring to kind of talk about 3.5 today. And then maybe the next day or so, maybe 2 days, we'll slow things down. We'll go back and revisit some of the stuff, talk about the types of problems that we've seen in the homework, and answer those questions. Okay? But 3.5 is talking about complex zeros and what we call the fundamental theorem of algebra. Okay? I think it's kind of interesting that this is ultimately your third algebra course, right? Algebra 1, Algebra 2, and then this. Okay? Pre-calculus is just algebra. Okay? There's a grouping, or there's a section of algebra that you don't know yet that you need. It's a necessity for being successful in a calc class. So they call it pre-calculus, but it's essentially just algebra 3. Okay. So you've taken 3 algebra classes, and now you're just finally learning the fundamental theorem of algebra. Okay. The thing that kind of gets the ball rolling with a lot of the algebra that we've done. Okay. And this is, you know, what I find interesting about mathematics and the way we teach mathematics is that in Algebra 1, you start learning how to factor. And you know that when I get an x squared, then that's going to factor down to 2 binomials, right? And then we've talked about how, well, x cubed is going to factor down to 3 binomials, okay, with x minus, plus or minus some constant, okay? And we go through all of that stuff, and we go through those procedures, those algorithms, those processes that allow us to do that, but never really talk about why, okay? And here's the why. This is why we can do this. It's the fundamental theorem of algebra. And fundamental theorem of algebra says that for every polynomial p of x, okay, with that format, okay, where all my exponents are integers, okay, positive integers, okay, and obviously my first coefficient is not 0, then it says you have at least one complex zero. Now we start talking about the complex coefficients and complex zeros. What we're used to and what we've been doing in the last couple days, our coefficients had to be integers. The rational zeros theorem says that you only can use this and apply this theorem if your coefficients are integers. Okay? So if I had like radical 2 out front, I can't do it. Okay? If I had pi out front, I can't do it. Okay? I can't use the rational roots theorem. Okay? But what this theorem says is that there should be still a technique that we can go through to factor things that have coefficients that are not necessarily just rational. They could be irrational. They could be, okay, when we talk about complex, they're really the thing that you should kind of think about when you see complex is I, right? Our real numbers, okay, encompass your rationals and your irrationals, but then when we see the word complex, that brings in another grouping of numbers and values, and that's the idea of A plus BI, okay? So we could have coefficients that look like that, okay? And those are ugly coefficients, but, and we probably won't deal too much with those. We might see 2 or 3 examples throughout the next couple days. But essentially, this theorem works for the entire complex number system. And it says whatever your polynomial is, that's however long it is, however many terms it has, you know that it has at least one complex zero. So I don't know the best way to write this mathematically, but it maybe it's helpful to see that if I have something, I'm just going to write the generic one here, x to the n plus or minus a sub n minus 1, x to the n minus 1. You've got some polynomial that looks like that. Okay? What this is saying is that every single thing that's in expanded form can be broken down at the bare minimum, something like that, where C comes from the complex numbers. Okay? Where you could take any polynomial that you want to, an expanded form, and you should be able to factor it down to a binomial to the first power, essentially. Okay? So x minus some complex number, plus or minus, ultimately plus or minus, this could be a negative number. So it could be x minus a negative number, so plus a number. Raised to some n. Okay? And we've seen some of this stuff, and it might be kind of, using this definition might be kind of arbitrary on what we're talking about, but every single polynomial should be able to at least be written this way. Okay? Now, it might be written something like this. Okay, we've been doing that kind of stuff, right? Breaking it down to those factors. Okay? But the fundamental theorem of algebra says it can be broken down to at least. It's going to have a bare minimum of one factor like that. Okay? And in conjunction with this theorem, which is called the complete factorization theorem, says that any polynomial of degree n greater than or equal to 1, can be broken down, okay, such that it looks like p of x is equal to some a, some scalar multiplier that just adjusts the y values, how tall they get, how compact they get, times a bunch of linear factors, okay? And, oh, I guess I can't write on here. The a, the c sub 1, the c sub 2, the c sub n, all those values come from the complex number system, okay? We like those c sub 1s to be like 2 and 3 and negative 5 and 1/2 and stuff like that. We like them to be rational numbers, but they can be, x minus 2i or x minus the quantity 3 plus 4i, something like that. But every single polynomial you come across can be broken down to a product of its linear factors. All right? And that's kind of what section 3.3, 3.4, 3.5 all kind of wrapped together are going to try to ask us to do. Okay? So we're gonna kind of practice this. What I want you guys to understand, and we're going to talk about this in a whole lot of detail last class, so we're going to have time. So I want to jump to it now. And it's called the complex zeros conjugate theorem. And what it says, all it says is that if the polynomial p has real coefficients, okay, and if the complex number z is a zero, so we end up finding that, 2 plus I is a 0. 2 plus I is a 0. Then its conjugate is also a 0. Does that make sense? Okay. So every time we do an example today, you're going to see, I think the first one they say I is a 0. And then the next thing they say is negative I is also a 0. They have to come in pairs. Okay. If 2I is a 0, then negative 2I is a 0. Okay. Algebraically, what becomes difficult is that when I say that like 2 plus 3i is a 0, that means that x is equal to that. Okay. The factor that came from would have been x minus 2 plus 3i. That's the factor. All right, we've got, if this was just like 5, we'd go x minus 5, right? Well, now it's a quantity, so it's a binomial, so we go x minus that binomial, x minus that quantity. But if that's a 0, 2 plus 3i is a 0, then x equals 2 minus 3i. Its conjugate is also a 0, and the factor that comes from would have been x minus 2 minus 3i. Okay, so that's kind of what we're doing here with the complex conjugate theorem. We'll talk specifically more about these types of questions tomorrow, and then the algebra that's involved with those. Today, I think all the ones that we see are just purely imaginary, so it's just like a 3i and a negative 3i. There's no real component to that complex number. Also, just some notation stuff. When we deal with complex numbers, In the complex plane, a lot of times specific numbers, we refer to them as z. Okay, so whenever you see z, they're referring to a complex number like a plus bi. And then whenever we put, there's a couple different notations that I've seen. The one that you guys will probably use the most is what's called z bar. Okay, that means z's conjugate. Okay, so if z is 2 plus 3i, z bar is 2 minus 3i. I took a complex analysis course a couple summers ago, and in that they used this sometimes, okay, z conjugate, okay, or I've also seen it used that way, okay, with that asterisk up there, just again, conjugate, okay. I think for the most part you guys will see z bar, and that becomes, I don't even know how much we use that in WebAssign right now with polynomials, but it will be something when we start talking about trigonometry. Trigonometry uses quite a bit of complex numbers. We'll start doing, you guys have talked about vectors and stuff like that in physics, right?
Yes, sir.
All right, we'll come back and talk about vectors in trigonometry. And when we want to graph a complex number, we know we can't graph the complex numbers in the real plane, the xy plane. So what we do is we take the y-axis out and we insert it with an imaginary axis, and then to graph them, we use vectors to graph complex numbers. Okay? It's really easy, but at that point you might see that notation of z-bar again. All right, so this is what we're doing. Let's do some examples here. All right, the first one says p of x is equal to x cubed minus 3x squared plus x minus 3, and they want you to find all the zeros of p. Okay, now, yesterday I told you you can kind of cheat sometimes and use your calculator to kind of get the ball rolling on a particular p of q value that might make sense to you to try, but then you still have to be able to do synthetic division. When we use our calculators and we look at the graph to tell us a zero from the graph, that graph does not tell you how that zero is going to algebraically kind of depreciate your p of x when you go through synthetic division, right? Some calculators will. I'll show you something here in a little bit that might be useful to you as you're maybe using this type of procedure as kind of the fundamental or the preparatory work for another type of problem. I wouldn't want to spend, if I have to factor something for a calculus problem, it takes me 10 minutes to factor it, but then it takes me 20 minutes to do the calculus question. I really wouldn't want to spend 30 minutes on a problem, right? So if I can spend maybe 30 seconds on factoring it, and then once I get in factor form, now I'll spend that 20 minutes on the calculus portion, that's a little bit easier, right? So I'll show you some techniques that we can use to quickly factor that without having to do any of the algebra. But I want you guys to understand that when we use our technology, we're not using it just to get the answer. We're using it with the mindset that we know what it's doing. All right, and when we get that answer, we know how that answer was created. Does that make sense? I hate using technology and not having a clue, just typing stuff in, not really having a clue of what's going on behind the scenes, okay, and why it's doing what it's doing. All right, so that being said, I think this one here kind of warrants maybe we talk about it using synthetic division, not using technology, because the p over q values are relatively small here, okay? If that's my function, p of x, okay, remember my p values are plus or minus 1 and plus or minus 3. They're the factors of negative 3. My q values are, again, plus or minus 1. Okay, so if I start dividing those, p over q, the only thing I get is plus or minus 1 and plus or minus 3, right? Okay, so those are my p over q values. Okay, so I'm going to start going through synthetic division. I don't know where to start. I don't know, is positive 1 a good place to start? Is negative 1 a good place to start? Or is 3 better? I don't know. So I'm just going to start with 1. Okay, but I do remember that it's important to look at your last line of work, your quotient line in the synthetic division, and that might kind of provide insight to you or for you in regards to what numbers to try. Okay, so I'm going to try this one, bring that down, multiply 1, -2, multiply gives me -2, that gives me -1, multiply -1 gives me -4, right? Not a 0, correct? Okay. I also look at that quotient line, and I don't see any of the behaviors that Descartes' rule assign, or I guess the quotient line is the upper and lower bounds. We kind of skipped Descartes' rule sign. Didn't really deal with it. Not a big deal. But this one, I think this one's even more informative. But I don't see the relationship that was provided in that upper and lower bound theorem yesterday. It said if you divide by a positive number, okay, and your quotient line is then all positive, we get a particular type of boundary, right? That doesn't happen here, okay? So the only thing I learned from that synthetic division is that positive 1 is not an option. So now I'm going to try -1. Bring my 1 down, gives me -1, gives me -4, multiply gives me 4, that gives me 5, -5, -8. Okay? Here is the benefit of knowing those upper and lower bound theorems, because now I know -1 is not a 0, right? -1 is not a 0, but look what these numbers do. Positive, negative, positive, negative. They alternate, right? So if they alternate, and I divide it by a negative number, okay, that tells me that -1 is a lower bound, telling me visually then on a graph that you will never have an x-intercept that is left of -1, which is really nice, because my other option here was -3, right? -1 is not a 0 anymore, and because it provided this logic that that's not an upper bound, or sorry, -1 is a lower bound, it makes sense that -3 can't be used either. Does that kind of make sense? So doing that synthetic division one time allows me to eliminate some pretty or it provides me with some pretty useful information. Okay, allows me to eliminate one more value. Now, generally speaking, those P over Q lists are a lot longer than just the 4 values that we had up there. So it would be nice if if I had like a list of 12 P over Qs, and I found out that my -1 did this, that might kick out 5, 6, 7 different P over Qs. Does that make sense, everybody? Okay, so it's really nice. But what's nice about it now is that we found out that +1 didn't work, okay, and that didn't really yield anything extra. -1 didn't work, and that yielded the extra information that -3 doesn't work, and now all you're left with is 3, right? So if this thing is going to have a real 0, because it might not, right? It might, or sorry, a rational 0. It might not. 3 might not be a 0, okay? But if we do have rational zeros, it's going to be 3, okay? That's kind of what this theorem says. So I'm going to try this, and the hope is that I do end up then with a rational 0. So bring my 1 down, multiply, gives me 0. 0, bring my 1 down, gives me +3, and there we do get the 0, right? So +3 becomes a 0, so x minus that is a factor. Agree with that? So x minus 3 is a factor. So the whole goal here is to try to break this thing down to its factors. So P of x, okay, if that's a 0, then x minus it is a factor, okay? And here again is the reason why we don't want to always rely 100% on our calculator in our graph, because again, our graph will not tell you that when 3 is a 0, what you're left over with is x squared, basically +1, okay? So we have to realize that that is x squared +1, okay? And what we end up with when we deal with any polynomial, okay? Any single polynomial is always going to be able to be broken down, be able to factor into a product of either all linear terms or all what we refer to as irreducible quadratic forms or expressions, okay? So this is a linear term and this is an irreducible quadratic. Does that make sense? You can't factor, when I say irreducible, we can't factor that any further, right? Okay? At least on the real number line. every single polynomial we come across is going to have that behavior. Okay, it's either going to be able to be broken down into a combination of all linear factors and all irreducible quadratic factors, or you might have all irreducible quadratic factors, so you might have another like x squared plus like 5 or something like that. Okay, but regardless, you should be always able to get any function down to something like this. But we can even go a little bit further if we bring in the complex plane. If we understand what the complex plane is saying, and the idea of a plus bi, those numbers, we should be able to go a little bit further with this. Okay? Think about x squared plus 1. A couple different ways of being able to find the zeros. Okay? Because that's what we did here, right? We found a 0, and then we knew what the factor was, right? X minus that. So let's look at x squared plus 1, and let's find its zeros. Let's solve that equation. Okay? A couple different ways you can do this. You can use quadratic formula, or you can use, because there's no linear term here, you can just do this. So x equals plus or minus just I, right? If you use the quadratic formula with this thing, you would go opposite of b, so 0, plus or minus b squared, which would be 0, minus 4a times c all over 2a. Well, that gives me plus or minus, what, negative 4 underneath the radical over 2. What's square root of 4? 2 square root of negative 1? I. So that numerator gives me plus or minus 2i. Bottom gives me 2. Is that still reduced to plus or minus I? Okay. So regardless of the route you go, you're going to get x to be plus or minus I. Those are zeros. Okay. Now they're complex zeros, right? They're imaginary. You don't see them on the xy axis. You cannot graph those on the xy axis. That's why they don't show up when we go to y1 and type this function and hit graph. Okay. This is the only one that shows up. Okay. But these are also important components. Okay. So if those are zeros, then the factors that they came from are basically, kind of working backwards. X equals, if I go positive I, move that I over through subtraction, right? And you get x minus I. Okay? We had x equals negative I. Move that negative I over, so you get x plus I. And there is your p of x. Okay? That is the complete factorization then of p. Okay? The real zeros are 3. The complex zeros are 3, I, and negative I. Okay? 3 is still complex. Okay? Just it lacks the imaginary component. Okay? But here's the argument. Here's the logic why we do that. And to see if this does hold true, you should be able to, because factoring is a fancy word for division, right? Foiling is a fancy word for multiplication, right? Okay? So factoring and foiling should compare to what division and multiplication compare to one another, right? Multiplication, division undo each other. So factoring and foiling should undo each other, right? So once you get to this, if I want to know if that's right, FOIL that thing out. Now, be intelligent about it, but once you FOIL that out, you should get back to that. And that tells you that you've done everything correctly. When I say be intelligent about it, is don't multiply those two together right there. Okay? Because when I multiply those two together, it's doable. I get x squared minus 3x minus xi plus 3i. And I got now a 4-term expression. I would then multiply that 4-term expression by x plus I. I'll eventually get some I squareds in there. Things will cancel out real nice. And I'll get back to this. But wouldn't it make a whole lot more sense to multiply those two things together first? Why? Yeah, what cancels out? O and I cancel out because those things right there are what? Conjugates. Okay? And there's kind of a visual of where that conjugate zeros theorem shows up and where it's used is that you found I to be a 0, right? Did negative I also come? Okay, so every time that you get a 0 that is complex, its conjugate is also a 0. Okay. Now here's the thing. I don't know if GeoGebra will let me do this. I know that TI-89 will, but let's say that we start with, and this is what I was saying, guys. Is at some point when you get to a calculus course, you're going to have to do that, for the preliminary steps of another calculus problem, and my hopes is that you don't, let me get rid of this thing, you don't spend 10, 15 minutes doing that. You know how to do it, you know where the work comes from, you can use technology to get a solution, but then understand what that solution looks like and see, did I use the technology correctly? Did it provide me something that I should have gotten? If I ask this thing, first I want to get that thing to go away. If I go factor, okay, a lot of like online calculators, you have to tell it the operation that you want to be done. If I say factor, let's say, first of all, when I hit factor, I get some options here to tell me the things I can factor. I can factor a polynomial, I can factor an expression in regards to a particular variable. That's kind of the one I want here. So it tells me the order that I got to type in. I got to type in what my expression is, and then I got to hit comma, what variable I want it to factor in regards to. Okay? So I'm going to factor, I'm going to go x cubed minus 3 times x squared plus x minus 3. And I want to factor in regards to x, and let's see what it does. It gets me down to x minus 3 and then x squared plus 1, right? Okay? I don't know that GeoGebra has the capability of showing me what the complex values are. Okay? It didn't obviously go x squared plus 1 down to x plus minus 1. Or, sorry, x plus I, x minus I. But you could do that on your own, couldn't you? If you need to go that far. So it at least breaks things down pretty easily for us. Okay? If we go back to what we talked about at the beginning of the class, that first question, we said this thing here was hard to factor because of the fact that the P over Q's didn't yield any zeros, right? Well, if I ask technology to do it, it breaks it down to these two irreducible quadratic expressions. Then you could use a quadratic formula with both those to get your zeros. Does that make sense? Or to get your linear factors. Okay? And one of those is going to provide you some imaginary ones. Okay? And the other one's going to provide you the two actual irrational zeros. But technology is very useful. Okay? But I don't want you to approach technology and use it without an understanding of what it's doing for us. Okay? You know, I get too many people, it happens all the time in geometry, and you guys did this in geometry, where you would take, because we weren't real confident in order of operations, we would take a calculator, and I would write something on the board, and you type in your calculator the exact same way I wrote it, and you get an answer, and you think that answer is right. Because the calculator did it, right? But who typed the stuff in? You did, right? Could you have made an error typing something in, and not necessarily know how that tool works, then not necessarily knowing whether that answer is appropriate, okay? Where if we understand what's going on behind the scenes, what is the algebra being done, we should be able to determine whether answers are appropriate or not when the technology does the work for us. Okay. Something else that could maybe be used here. Now I don't know. I don't know what GeoGebra is going to do here when I type in I. So x minus 3, x minus I, and then x plus I. Okay, so it just didn't simplify things, right? I squared, negative I squared is that, I squared is a negative 1, right? So it's a negative times a negative 1, a positive 1. So that's a positive x right there. Look at your original function. Is that a positive x up there in the red? And then we got 3i squared. Well, I squared is a negative, so this is actually a negative 3. We have a negative 3 up there. And then you got x cubed and negative 3x squared, right? So it doesn't have a great ability. Maybe even if I do this, I don't know if this will work. It probably doesn't know what to do here. Yeah. But you can read into what's supposed to be being done there, right? You can check using technology that you've done this correctly. Your TI-83 or 84 does not do that. It will not FOIL for you. Okay. The TI-89, if you have one of those, which I hope you don't, so this course doesn't let you have one. But if you have a TI-89, that is something that that calculator will do. The TI-89 is just kind of, and your professors will tell you this, if anybody ends up, you know, you want to be a mechanical engineer or something like that, or chemical engineer, really any engineer, you're going to take some math courses, probably some high-level math courses. You'll go through Calc 1, Calc 2, and in some of those courses I've had, you guys know, you remember Lindsay States? Okay, she came back a couple years ago and told me I think she's at Miami, is that right? Okay, she came back and said, hey, my Calc 1 course, 16 weeks of no calculator, absolutely none. Okay, so your Calc 1, your Calc 2 course, that's the way my Calc 1 course was in college. We weren't allowed to use calculator, okay? Even if I showed up in class with one of these, it was a problem, okay? That's why I try to, focus on that idea when you're in Algebra 1 and Geometry, said don't use a calculator, because at some point, you might get into a Calc 1 course, and a lot of majors anymore ask you to take Calc 1, okay? You get into those. My sister's a pharmacist, okay? My sister's a pharmacist, deals with, medicine all day long. She had to take Calc 1, okay? And you just never know what your professor's preference is going to be, whether they use a calculator or not. Where is it? Oh, so you get to further calc courses, you're going to want to be able to do a lot of preliminary algebra. So you're going to want a TI-89 because it does everything that you learn in Algebra 1, Algebra 2, and Algebra 3. There are functions on that calculator that you can type it in, and it does everything you need it to do. Factors anything, factors it down into complex numbers, all that kind of stuff, gives you all your zeros, your roots. It's very, very useful. Solves any equation you ever type into it. But the reason we have those is because those solving those equations and those factorings are preliminary steps to get to the more complicated calculus, right? We don't want to spend a half an hour solving a system that then I'm going to use those solutions for a particular calculus concept. We'd like to solve that system in an instant and then spend all our time on the calculus. So that's what you'll do if you decide to take higher level math courses. That being said, technology is awesome, but we got to know the appropriate way to use it, when to use it, and all that kind of stuff. I want to get down to an example here. If you read through these slides, it just gives you an idea. And we talked about zeros and their multiplicities with rational zeros. Multiplicities can occur, again, with your complex numbers. You see here with this function, x to the fourth plus 18x squared plus 81. We have factors to x minus 3i squared and x plus 3i squared, or quantity squared. So you see that 3i is a multiplicity of 2, negative 3i is a multiplicity of 2 as well. But also what you should pay attention to is 3i, its conjugate is negative 3i, right? So they came together. Up here, this one here had conjugate, I was a 0, negative I became a 0. Conjugates again. Okay? You're always going to see them show up in pairs as conjugates when you factor these things. That number 4, that fourth degree polynomial in here, you had the ability since like week 1 to factor this thing. You guys remember using U substitution? That's kind of the approach that we would use here with this one, to factor down to see that we get x minus 3i squared and x plus 3i squared. Something they're going to ask you to do in your homework is question A here, okay? Where they give you the zeros. They're telling you, here are the zeros. Maybe you look at, there's different ways of them providing it. Maybe you look at a graph. Maybe they give it to you in sentence form, whatever, okay? But somehow they will tell you what your zeros are. Now, if you're looking at a graph, obviously, graphs don't have your imaginary or your complex solutions, right? Your complex zeros. So, if you're looking at a graph and complex zeros do exist, they'll have to write that out in words for you, okay? And they'll have to tell you that use the graph to find your real zeros or your rational zeros, and then use this additional information to incorporate your complex, okay? What I don't like about this question is they pretty much provide us everything we need. If I look there, come on, all right? They say I and negative I, right? Okay? A lot of times in your homework, they're going to say, here's a fourth degree polynomial. Find the fourth degree polynomial where you have zeros of 2, negative 2, and I. Well, that's only 3 zeros I gave you, right? You have to use the conjugate's theorem that says if they gave me I, then what also has to be a 0? Negative I. Okay, so they always hide one of your zeros with that conjugate's theorem. Okay, but this one is a little bit more explicit and gives us everything we need. So let's just write down what we've got here. We got P of x, okay, That's what we're trying to come up with, and I want to eventually expand this to polynomial form. Okay, so we should be able to quickly write this in factored form. What the fundamental theorem of algebra and the complete factorization theorem of algebra basically says is that we should be able to, with 4 different zeros, we should be able to break this thing down to essentially 4 linear factors. Okay, where this is x to the first, x to the first, x to the first, x to the first, right? And then plus or minus whatever my zeros were. Okay. Now, if those are my zeros, it's going to be x minus that 0, right? So let's start with the real zeros. Let's start with 2 and -2 first. Okay. So if I go x equaling 2, 2 being a 0, then x minus that is the factor. So 2 is the 0, x minus 2 is the factor. Okay? Go to -2. -2 is the 0, so x minus that, so x minus -2 is the factor. Minus the -2 becomes +2, right? Okay? Then we get to the imaginary components, and I is a 0, so it's the same logic. X minus I then is also the factor. And if -I is a 0, then x minus -I, which becomes x plus I, becomes my factor. Okay? And that is the factored form of this polynomial. Now, I'm missing something here because of some logic that we've talked about in the past. If I've got, I'm just going to use some arbitrary function. If that's my function with those zeros, is there a function that might look like that has the exact same zeros? Yeah. Is there a function that might look like that has the exact same zeros? Okay. And the only thing that's different amongst those 3 functions with those zeros is maybe for some x, let's just call it x sub 1. The y values that go with that are different, right? And the only way that we can change those y values is if we multiply those y values by some scalar, okay, some multiplier. And that multiplier, that thing that stretches or compresses our graph vertically, we're going to call it a. Okay. If they don't provide you extra information, you let a just basically be 1, and it makes things really easy. But there's extra information right there. Okay. They're telling you a point that your function on your graph has to go through. It has to pass through x being 3 and y being 25, or p of x being 25. Does that make sense? Okay. So that's information to plug in here to find that a. So they're saying p of x, when x is 3, that number there, when x is 3, is 25, right? Well, when x is 3, that makes this here 3 minus 2. That makes that 3 plus 2. This makes this 3 minus I, and it makes that 3 plus I, doesn't it? All right, so what we have there is ultimately a product of a bunch of real numbers. Okay. Now these are complex, but what happens when I multiply those together? What's 3 times 3? 9. Negative I times I gives me negative I squared, but you guys know that's positive 1, right? That becomes a negative 1. 9 minus negative 1 gives me 9 plus 1. So that when I FOIL that out becomes 10. Gives me a real number. Okay? This is 1. This is 5. This is a, and that's 25. So they give me 25 is equal to 50a. A then is a half. Okay? So I know now that number right there is 1 half. All right? Now, we're not done because the goal, and you just got to pay attention to the directions that WebAssign is asking for or the test is asking for. They might say, fully expand this, write it in polynomial form. Right now, that's not polynomial form, that's factored form. Okay? If they use the word factor, it means break it down to something like this. If they use the word expand, that means put it in polynomial form. Okay? So we want to multiply this together. Now, again, be intelligent about what you're multiplying together. Hopefully you realize those two are good ones to multiply together first, right? Because they're what to one another? Conjugates. So I get x squared, what, minus 4? So I got my 1/2 out there. This thing here, x minus I, x plus I, x squared plus 1. Okay, so still not done because now I've got these two binomials I can FOIL, right? And basically that's what happens. And the more, and obviously the 4th degree is cumbersome, it's a lot of multiplication. But think about what happens if this is 5th degree, or 6th degree, or 7th degree. All the extra additional multiplication has to be done with those things. X squared times x squared gives me x to the 4th. X squared times 1 gives me x squared. Negative 4 times x squared gives me negative 4x squared. Negative 4 times 1 gives me negative 4. Still got my 1/2 out here. Combine like terms, I get 1/2 x to the 4th minus 3/2 x squared minus 2. There's my original P of x that provided those real zeros of 2, negative 2, negative 1, and 1. Or sorry, negative 1i and positive 1i. Okay? If we were to graph this, if I was going to GeoGebra or my TI 384, graph that thing, and go to my table and ask it for x to be 3, it'll give me back 25. Okay, I'll see that point on that curve. If I didn't have this 1/2, if I just had x to the 4th minus 3x squared minus 4, 325 is not going to be on that curve. Okay, the 1/2 is going to force that 325. I think going through this route, okay, because it's kind of backwards of what we've been doing, right? What we've been doing, we started with this and went to that. But if you can go from this and get to that, I think it gives both kind of procedures a better understanding. It gives you a better understanding of both procedures, which is useful.
Teacher's pardon the interruption. After this period, any student who's interested in playing football next fall